Yeah, let's start by discussing the challenges. So this is an illustration of Sora, what a confused person or troubled person should look like. So what are the problems? What are the open points to address based on what we've discussed so far, basically? From our perspective for physics simulations, I think the key things that are in a way missing with the current state of the art is scaling these techniques to real-world problems. So we've discussed quite a few examples. I'm sure you're also aware we had practical exercises and things on the slides. Interesting cases, but nonetheless for real-world industry problems, a whole car, right, a motor block, an engine of a plane or so, we're pretty far away from that. And that is also still a problem with the state of the art in research. So making that step from the problems that are relatively easy to solve to actual things that help people in industry, with real world problems, is still quite a step. And there are two aspects to this. One is just training the models, right, preparing something that could be used then. Potentially this is even the larger hurdle at the moment, right? Because for this stage, we actually need not just one example, we need a whole training data set that should capture all the behavior that we'd like to use a trained model for afterwards. We need to just load, we need to store the data, just all these processing stages are really resource intensive. That's basically one of the aspects here. And then the sample efficiency is also basically capturing the problem that we might need a lot of data. So it's in a way still an open challenge how to get the most out of the samples to train with as little as possible. Right, so if we could train with few samples, the resources would go down. If we need a huge data set, then this becomes that means we had bad sample efficiency and this becomes a problem. So this can be gigantic. Once we've trained the model, nonetheless also, we still need to compete with existing solvers. So even at inference time, once we successfully train the model, it is worth checking at how much compute resources and memory we still need to run the model once. Good example are current LLMs. It's available for free on the web, but every execution of one of the GPT models and so on actually costs a lot of resource in terms of energy, and there are estimates of what OpenAI pays currently for every query that is posted online that's answered for free, but it's probably quite resource intensive. And of course, in any other discipline, right, if we go to prediction rate of a flow around a car or so, it's also how much resources are needed to get that one prediction. That will still play a role, and I think there's a lot of room for improvements. Yeah, going towards these practical scenarios also, if you ask anyone in industry, they're rarely working with regular Cartesian grids. It's something that is refined, right? On the surface of some object, we have very fine meshes. Far away, we want to capture a large surrounding. You might have complicated geometries, very fine details, right? Complex inflows, outflows for medical conditions. Capturing all this typically requires unstructured meshes, so given in terms of tetrahedral meshes, or at least going away from regular Cartesian grids, and processing these is also arguably still a challenge. We've discussed graph nets, but that's also not exactly cheap. It actually is quite a bit more expensive than CNN, and whether that's the end of the line remains to be seen. Our nature is three-dimensional. In addition, we typically have things that change over time. So ideally, we actually, for many problems, need essentially four-dimensional solutions that capture 4 dimensions, 3D over time. So, if you can do one 2D snapshot, that's a good starting point, but adding 2 more dimensions for third spatial dimensions and a time dimension adds a lot of complexity. But so also what we hear from industry partners, these 3 topics together are really requirements that are currently missing in many papers and in many of these existing techniques to get these into real-world applications. There's another fourth point that I do want to mention that is also playing an important role for the whole field. In terms of theory, our understanding of these, that is a bit detached. I'll come back to it later in a moment. Nonetheless, I think an important one to mention. Starting with these first three topics, I do want to give a bit of an outlook in the form of these foundation models, how to address these open issues given our current understanding of what's possible. And right, this is not the end of the line, right? I think it's an outlook, so please keep that in mind, but I'll give you the best of my guesses how to approach that in next years. Time will tell whether it's actually correct or not, but I think we'll see pretty soon because the field is changing so quickly. But my current guess is that based on the transformer architectures, we will actually be able to address quite a few of these shortcomings. So they are already very widely used. They're shown to scale quite well. So actually better than CNNs and graph nets in practice. That is actually, I think we mentioned already a couple of weeks back, why they're so popular in a way. They can do fundamentally different things than what you could also do with a CNN or a GraphNet, but scaling them up to really huge sizes and doing so without computational and memory costs exploding is something that is right now actually given with transformers, but difficult with the other two. The data efficiency is also something that could potentially be addressed in the context of these foundation models by pre-training a large model and then fine-tuning it with a smaller data set. So the hope there is that if we set this up correctly, we have a large enough data set, we can actually pre-train something that has learned the key challenges, the key dynamics for a certain area, and then these dynamics can be, or all that's necessary is adapting these a bit to then be able to produce solutions for a new problem setting. So most likely, right, there are limits. So good example are the large language models. Have been used for things like physical predictions or other things. They're really good with language. They have their limits in other domains, but for example, a new language, typical structures of human languages seem to be really well encoded in these models. So if set up correctly, I think there is a good hope that with a suitable data set for a certain domain, like fluid flows or structural elasticity, that you can pre-train a model that captures most of the important things and then is able to do new tasks in that surrounding. There is actually a nice example here in the form of the Aurora model from Microsoft for weather that essentially pre-trains weather on our Earth geometry, but right, our Earth doesn't change that much. So for the next years at least, probably most of the mountains are going to stick around, the shape of Europe is going to stick around and so on. So in a way, pre-training how our atmosphere behaves on our planet seems to be captured quite well in that model, and they were able to show some interesting new tasks for like pollutants and other tasks that were not directly trained for, at least on that geometry basically. So this is an example of the kinds of transfer that I think are potentially also interesting for other fields. Yeah, and ultimately another advantage will be in the next years, we see this explosion of activity and work on transformers in the context of LLMs. Using all that in other disciplines will naturally also pay off. So the whole infrastructure that is currently built around language models is also something to be leveraged for other disciplines. Yeah, how could that look like? I do want to show one example that we know well from one of our own works. So we've looked at transformers and basically how to piece together the best of the vision and pattern recognition fields for something that works for PDEs. And this is one solution that I think does work quite nicely. So this is an overview. The core transformer structure with attention stays the same. So if you start here on the the left-hand side, we basically have, this is the conditioning, here is the main input. It's processed into a sequence of tokens. In addition, we have a conditioning, say on a hyperparameter or something that comes in. But the main transformer stages at their core are similar to before. So we have attention on these tokens being computed. One thing to point out here that is very useful for PDEs is that indicated here by this triangle, this hierarchical. So we start on a certain resolution, then downsample this, do some more processing on a coarser resolution, in this case 3 levels, some additional processing, and then similar to UNet, in the context of transformers, go back up to the original resolution here. Ultimately, right, improving the processing on different granularities of the representation. Now, for the transformers, I've also mentioned before, one of the kind of bottlenecks typically is attention. And the self-attention mechanism processes these n tokens and leads typically to a dense matrix of correlations. Matrix being dense means it's n square. So we have a squared complexity for the basic attention. A neat way to circumvent that is what's called SWIN, shifted window attention. It's mimicked a bit here in this box. The idea is that we don't need to, in one go, have global communication, but ultimately, after multiple steps, a bit like CNNs, effectively, propagation should be across the whole domain. However, to get away from the n-squared complexity on the whole data, we turn to local windows. So basically let attention be computed in a small window. Then we have still complexity of n squared, but now not with respect to the whole data, but just with respect to that smaller window size. This we do for lots of these small windows. And then in a second step, to make sure that everything is processed, we shift these windows. Hence the name shifted window attention. It's a bit similar to convolutional kernel in a CNN or GraphNet. So that does work quite nicely and gives us better scaling. So we have a hierarchy. We have this scaling, or we got rid of the really bad scaling of the core attention mechanism. So that's replaced here. The rest is relatively similar. It's also the conditioning over normalization layers, and the basic structure is preserved here. A variant that, here I do have these on the slides, turned out to be useful is for physics problems. We typically don't just have one stream of words or RGB or so, but there might be different input quantities. So you might have velocity, the next one velocity, temperature, and some additional transported fields or so. For the flexibility on this channel side, it actually turns out that it's a good idea to split these the processing with these SWIN transformers for each channel. So don't embed all these channels directly into the embedding dimension, but let them be processed separately, and then have a channel-wise attention step that goes basically across these different separated channels as a separate operation. And in that way, you can later on change what's encoded in these different channels. So for PDEs, that's potentially an interesting extension. Yeah, we did look at this right in the past months, basically, and now to give you some hint of the capabilities here for flexibility and improving sample efficiency. This is now one example where 2 variants of 2D versions of this transformer were trained on a also larger data set of basic PDE inputs, and then were applied to new cases with smaller data sets and a bit of fine-tuning. So fine-tuning meaning we basically load this pre-trained model, then with a very small learning rate for a shorter duration, retrain the model to adapt to the new outputs. It's trained on a big data set for a long time, and then we have another fine-tuning phase for a new data set, and these were now three completely different PDEs that were not contained in training data from an external data set called the well. And this now shows along Y the amount of improvement over the basic model. And the red ones now are the ones that processed all these input fields together, whereas the blue ones now show this variant that had basically dedicated processing for each of the channels, this separate channel version. And as you can see here, especially for these two tasks, for this first one, active matter, it didn't matter so much. The overall improvement was not large. Actually, the difference between these two versions is still significant, but especially for these RBC and shear flow data sets, we have improvements of 30% and more over the basic version, which is a neat improvement in terms of accuracy. And this is now basically done with a relatively small data set, so potentially pre-train even more, hopefully with an even larger data set. There is definitely hope to leverage these fine-tuning approaches also for physical problems. With the same architecture, we're also able to show that this can be extended to 3D. So this now does become quite expensive to train. The previous case was still 2D, but the basic architecture, if you apply these to 3D problems on sufficiently large GPUs, which luckily now the compute centers can provide, then we're able to scale this up to 512 cubed for an isotropic turbulence data set. And I think that's approaching the problem sizes that would be relevant for practical applications. So this is still on a regular grid, but nonetheless has more than 400 million degrees of freedom. So that's almost 500 million their size, I believe. Yes. Yes, exactly. Exactly. The basic architecture is the same. So one change here was that this model is pre-trained on smaller regions, basically, in this case 128, because 512 cubed training that directly would make every, if you have a batch size on top, would make any current GPU explode. So this was pre-trained on smaller 128 cubed regions, and then these were linked together with another network that we called context network. But breaking this down with another level of modularity was able to scale this up to these fairly large sizes. So also a potential outlook for scaling these up. Yeah, I've mentioned it, this was on a regular grid, so obvious next step is also for these architectures to work with unstructured meshes. The image here should just show, typically we have tetrahedral, potentially very complicated geometries that conform to some shapes, potentially encode intricate small-scale features. So this is from a statics stress simulation for materials, but these similar structures you encounter in any complex real-world problem, I believe. So yeah, this is necessary to accurately encode and work with obstacles in flows or in other materials to specify boundary conditions or to resolve regions where we know here the solution is extra critical and important. And for real-world cases, often constructing these meshes is actually approaching the time, or sometimes even exceeding the time that you need for the physics simulation part. So computing just one of these mesh structures on which to simulate the physics can be very expensive. And dealing with these in the context of these neural network models is likewise a challenge. I think also here transformers are a natural way to go. They typically have position embeddings, they potentially can yield solutions not just at exactly predefined regular grid locations or so, but they already typically work in these attention mechanisms with encoded positions. There were a couple of works already that show that basically you can query these solutions at different points. And I think likewise this is a promising outlook, but how to best work with large, complex shapes like this is a topic of ongoing research. I think we're going to see quite a bit of work on that front in the next years still. Yeah, I do want to mention this fourth point, the theory. Right, this is a bit beyond the scope of this lecture. We focused more on the applied side of how do we actually get towards real, kind of at least learned simulators and somewhat real-world applications. Theory, nonetheless, is a very important foundation for all of this, so I do want to mention it here. Right? Traditionally, linear cases have been studied extensively in math. We have, I would argue, so not fully solved, but I think we have very good understanding of how linear cases work. So kind of approaching this level of understanding and the theory that we have for linear cases for nonlinear ones is a big to-do list. Nonlinear cases are fundamentally more challenging. We have much less in terms of fundamental theorems and things we can build on, so it's work in progress, but this definitely does require more work. I think, especially in the past, people have often complained, right, neural networks are black boxes, we don't understand them. I think with these comments, people often overlook that a lot is happening. Our understanding is improving. It's just not a difficult, it's a very difficult topic. It's not done in half a year or so, but right, I think this is no reason to panic or say, or it's all worthless. It's just something that needs a bit more time, and a lot of smart people are working on it. So I'm sure also a lot of progress will be made here in the next years. So, right, common question in this context is, right, for linear solvers, I have convergence guarantees. Well, typically they're also for pretty confined and idealized cases. If I go to real-world settings, many of these guarantees are lost. I have additional approximation, uncertainty, floating point errors, and so on that come on top. Nonetheless, it's an easy thing to ask for or to complain about, right? Where's my convergence guarantee for this learned solver? I do want to mention that these hybrid approaches that we've discussed, that basically combine a classic one with a learned one, do offer certain guarantees, depending on how you set up your approach. If you, for example, first let a network, for example, produce a correction to a certain state and then run a classic solve, say for divergence freeness or conservation laws, after that solve, you actually have the guarantee that up to numerical precision of the classic solve, your solution does satisfy divergence freeness, potentially you could guarantee other conservation laws. So we can actually leverage that. And I think that's exactly one of the strengths of this combined approach, that if we work with classic solvers and combine them with learned techniques, we actually can leverage a lot of the existing knowledge about classic solvers. So just as a side note in this context, another reason for working with both sides kind of hand in hand. Yeah, nonetheless, a big area and worth lectures on its own. I do want to attempt a global summary for our course here. So we've covered a wide range of topics, just to have them on the slides again, starting with a supervised approach that's working with data, incorporating PDEs and physical priors into losses or directly into the inference and training process. We've looked at the unstructured inputs in the form of graphs, then at somewhat orthogonal topics in terms of holistic modeling with the diffusion models, and then also last week with the reinforcement learning as also in a way a different classic perspective on learning problems that nonetheless shares a lot of similarities and can potentially solve very similar problems to the ones we've previously approached from the machine learning side. Yeah, and today this outlook towards larger foundation models. As a global outlook, I do want to mention that we actually have very good solvers, and I think it's clear that for certain areas they are just ideal solvers. So my guess is also that for specific, probably somewhat narrow, but nonetheless certain areas of solutions, classic solvers will be ideal. To give one specific example, there are spectral solvers, right, working the frequency domain, that are just in a way perfect for certain types of linear PDE problems. They have essentially exponential convergence. They converge super quickly to pretty much any accuracy that you would need. Right, they scale great. They're super accurate. So, right, it's basically for numerical methods perfect. And I don't see any chance for networks to outperform that level of quality and accuracy with the current approaches in the field. But in a way, that's also not necessary, right? These don't work for all kinds of problems. They work for certain narrow, right, typically right, fairly idealized periodic cases, not too complex boundary conditions and so on. For these, they're great. In a way, the interesting challenge, and I think also what's happening at the moment, is to find out where the learned approaches really work well, and potentially that's in the cases beyond these idealized conditions where, say, these spectral solvers are super good. Right, areas with nitty-gritty details I put here on the slides, right, but basically somewhat more less idealized conditions with complicated boundaries, with uncertainties, and noisy measurements are another good example. So I think there are actually many real-world cases that feature some or many of these challenges, and where suddenly these idealized spectral solvers are in trouble, and again need a lot of work or special additional stabilization terms or couplings with other methods to get a good solution. So suddenly these very attractive techniques break down to some extent, and exactly in these areas I think there is a lot of potential for these learning-based techniques. Nonetheless, right, some areas might remain where the classic ones are just unbeatable, and we should keep on using them, right? If we have a really good tool, why not use it? But for other areas, I'm sure we'll find areas where actually the learn techniques will provide much better solutions in the future, and also will carve out their dedicated areas where they'll stick around to provide the perfect, it's arguable, but at least very good solutions, and will provide helpful tools to advance different fields. Yeah, so to put that into somewhat pro and con bullet lists that we had for the individual topics, I think it's definitely a powerful and very interesting new methodology with a very promising outlook, right? As mentioned before, there are challenges. We're not there yet that we can directly throw any problem at these methods, but it's definitely very promising. Open challenges remain, and also I do want to mention that even if we have a breakthrough now and suddenly these methods work, right? Suddenly we have a very efficient pre-trained model that solves a certain class of problems really well. For many industries, for many environments and companies, there are very established workflows. So I just want to mention this is not a possible challenge, but just establishing certain techniques in disciplines takes some time, right? The classic solvers are validated. People know how to set hyperparameters, how to check the quality of solutions, have the compute infrastructure and so on to run these things. And for neural network-based solutions, that is probably still missing in many companies, so that will take some additional time. But in a way, this is just a matter of figuring it out, waiting in a way, or working out the details. There are more interesting challenges for research on this side of the challenges, but nonetheless, I think it's definitely an exciting field at the moment. And this is really also my last slide for the content. So thanks for sticking through all the weeks so far.